Welcome to the Cannabis Cultivation and Science Podcast. I'm your host, Tad Hussey of Kiss Organics. This is the podcast where we discuss the cutting edge of growing from a science-based perspective and draw on top experts from around the industry to share their wisdom and knowledge. Some quick updates before starting the podcast. It's been a little while since my last podcast due to our hosting the first Cannabis Cultivation and Science Conference in September at Collective Elevation in Bozeman, Montana. There were some amazing growers, researchers, and experts I got to connect and personally network with. And for our first conference, I felt like it went as well as it possibly could have, and I'm excited to plan for the potential of hosting it again next year. We have not officially confirmed for 2026, but the unofficial dates would be the last weekend in August of 2026 if you want to mark your calendar and plan ahead. Some other news is we've added a bunch of new IPM solutions on our website. We are official distributors of Bioworks now, meaning we can sell EpiShield, Sufoil X, Root Shield, Principle, their new Bavaria product, Cease, Millstop, and everything else they offer. I have direct access to their pathology and science team and can put facilities directly in touch if it's helpful. In addition, we also carry Actinovate, Azagard, Grandivo, Pyganic, Regalia, Sanidate, PFR 97, and much more. Our pricing is lower than Arbico, and we can do custom quotes on the commercial side. We have also added heavy metal testing on our website through a partnership with Cannabis Chem Lab for only $99 a test. They are an ISO accredited laboratory and can test soil, fertilizer, water, and plant material for common heavy metals. This is the most affordable testing option for heavy metals, so you can make sure you're in the best position to pass in some of the tighter regulatory states. Now on to this week's podcast. I'm very excited to share my conversation with Dr. David Hawley. In his role as Fluence's principal scientist, Dr. Hawley steers the company's global cannabis crop sciences program, encompassing photobiological research, data analytics, and cultivation consultation. Fluence's research has identified specific and diverse lighting strategies that consider crop yield, morphology, quality, and economics that maximize commercial growers' objectives, whatever their crops and production objectives may be. David is a passionate advocate for scientific integrity in the horticultural industry and brings this passion to the design and execution of Fluence's studies, several of which are published in peer-reviewed journals. These studies form the foundation of Fluence's products and drive Fluence's mission to service the global horticulture industry with objective, evidence-based lighting solutions and education on what to avoid. Now on to the show. Hey, Dr. Hawley, thanks for coming on the show.
Hey, Ted, thanks for having me.
Yeah, absolutely. I've been wanting to have you on for a while now. I met you a number of years back at PhotoX, and a lot of people may not be familiar with what PhotoX is. Do you want to touch briefly on that and tell them a little bit about yourself too?
Yeah, absolutely. So my name is Dr. Dave Hawley, and I'm the principal scientist at Fluence, which is a horticultural lighting company. I joined Fluence in 2018, and I came from the world of academic environmental science. I was working at the University of Guelph developing lighting solutions for growing plants in space, and then started working on cannabis and plant secondary metabolism, and joined Fluence with the shared sort of vision and the shared values of helping the world grow smarter. That's our tagline, and we stand by it. And we aim to achieve that simply by doing objective scientific research and then making products based on what that research tells us. So PhotoX is kind of a celebration of that. It's candidly, it's not so different from a lot of academic science conferences, but we really try to have PhotoX be this summit of horticulture science that bridges between academic and industry applications. So exposing people to the bleeding edge while also translating some of the more academic bleeding edge stuff to commercial application.
Yeah, it's a lot of what I also try to do with my podcast, this idea of simplifying and having a broader reach for science so people can see what's being done out there and getting it out to them so we could make better decisions in our gardens. So
Awesome.
I had a great time. And I remember when I was there the first time, I learned a ton of things. And we also talked about, you showed a bunch of peppers from your growth chambers and how different lights affected the morphology of those peppers, how they grew was substantially different based on the spectrum. And I want to talk about spectrum, but I'm getting ahead of myself. Let's just start off right off the bat with some real basic lighting concepts or things that science has sort of proven over the years around lighting. I kind of want to start with lighting intensity.
Sure.
So there's this idea that was expressed at PhotoX, more recently this year, that essentially 1% more light equals 1% more yield. Now, I realize this is a very broad generalization. It's going to change based off of cultivar, environment. There's a lot of variables that go into that. But can you talk a little bit more about that just as a general statement?
Yeah, totally. So this idea that 1% more light translates to 1% more yield holds true in most plant species. And people really started talking about this in like recent years when Leo Marcellus from Wageningen University published this and started talking about it a lot in the context of tomato. He's not the first person to come up with this, but he's the first person to kind of bring it to light, at least in the common kind of vernacular of modern horticulture using LED systems and so on, which really have changed the way people talk about lighting. Honestly, it's such a fundamentally different technology from high intensity discharge lamps or incandescent that came before that. But as it pertains to cannabis and the way that we've been talking about it at Fluence, it's interesting because cannabis can take an awful lot of light, and this 1% more light is 1% more yield thing is true up until a point of photosynthetic saturation. And that ceiling is different based on your species. So like with tomato or cucumber, that ceiling might be around 300 micromoles per meter square per second. With strawberry, that ceiling might be around like 600 micromoles. With cannabis, that ceiling's more like 2100 micromoles, for example. So it's like an order of magnitude more light than you could put on other species. And it is important, like you mentioned, that there's cultivar dependence and interaction with other climate factors and so on, and that's very true. So in the case of cannabis, for instance, when we had this result, uh, we saw it across three different spectra and three different cultivars. But if you were to look at the individual data for like one spectrum and one cultivar, that trend that we're talking about might not be accurate. It might be like, well, I didn't really get 1% more yield for 1% more light. You lied to me. It's like, well, no, I didn't. If you look at this other cultivar, you'll saw that you actually got 150% more yield for 1% more light. And on this cultivar, it's exactly 1% more light is 1% more yield, and so on and so on and so on. So when we make these sort of generalized statements, like 1% more light is 1% more yield, we're talking about kind of like a meta analysis that is pooling a lot of data from a lot of lighting scenarios and a lot of different genetics to say, okay, on average, this is the response that we talk about. And then that response can be attenuated based on whether there are other limiting things in the environment. For instance, if you're driving plants really, really hard, that means they're going to transpire a lot, right? It's kind of like plants sweating. They're moving a lot of water up through the roots, through the vascular tissue, and at the leaves to cool themselves down. But all of that water goes into the air. And if you're not managing that humidity load, then the plant slows down. And then it doesn't matter how much light you add. If the plant can't transpire, it can't cool itself down, it won't photosynthesize efficiently, and you won't put on that yield, and you won't get that one-to-one return we're talking about. So, a simple statement with a lot of complicated stuff behind it.
Yeah, and I remember Dr. Bugby presented, I want to say 2019 was my first year at PhotoX. And in his talk, he talked about how cannabis is a highlight plant, similar to corn. Basically, the more light you threw at it, the more yields went up, provided all other environmental conditions were optimized.
Mhm.
However, there was also research at the time from Dr. Allison Justice that she did in her facility, essentially showing that there is an intersection between yield and PPFD, par levels, where yes, we may get an increase, but that increase slows down potentially, or the cost to produce the electricity to get that yield increase made it not worthwhile from a commercial perspective. Has that research changed, or because I remember at the time we kind of were landing around 1,000 ppfd, I think maybe 1,200. Where are we at now with that in terms of what the research is showing you?
Yeah. So I'm not familiar with Allison's research specifically on that, but I think I understand the spirit of what's behind that, which is that, again, I hate to be long winded, but there are a lot of complicated things that affect whether or not it's economically optimal for you to add light to your situation or not. And I'm just going to start there because that's the relatively easy kind of thing to pick on. For context, right, there are growers in Ontario where they're paying 3 cents a kilowatt hour for electricity. For them, energy is basically free. And so if they just keep putting more and more energy onto that crop, that's all profit, you know? And I'm exaggerating a little bit, but like they're not paying for that energy and they're just dumping it into the crop, and that's great for them. Um, Conversely, there are growers in New Jersey and in California and in parts of Western Europe where energy prices are up to 38 cents kilowatt hour, right? Like that's really, really high. And so you need to make a very careful decision and do an economic analysis to say, for the value that I get for my harvested product, whether that's a tomato, whether that's A bud or B bud or C bud in the case of cannabis, or any other crop, am I making enough revenue to justify the added expense for me to spend more money on electricity, put more light on this crop, and everything else that goes with that, right? If I'm pushing the crop harder and I'm growing bigger plants, that's going to affect my labor. It's going to affect my HVAC. It's going to affect cycle time. So it's not as simple as just saying everybody should just put more light on their crop all the time and then make more money. It's like, yeah, you will, but you'll also have more costs in a lot of cases. It's a very case by case thing to assess whether or not more light is always best. But in general, if I had to generalize, I would say, at least in North America, the market value of cannabis is so high that for almost everyone, it makes more sense to put more light on the crop and get more yield.
Yeah, as I think about it, it's the analogy I've used in the past talking about this is sort of like it's like driving a sports car really fast down the road. Like yes, you can go faster and faster, but everything has to be dialed in. If you're not providing sufficient CO2, then you're not going to get the photosynthetic effects that you want from the light, and you're wasting energy. So it all does play together, and you're also more likely to see a dramatic change in the plant if you screw up, if you're running really, really high par levels. So I just think like, yeah, if everything's dialed in, then yeah, we could go with higher levels. But what do you think is a good range for the average grower, keeping in mind that our listeners may be anything from a home grower with 3 plants to, someone with 3,000 or 30,000 plants in a facility? Uh, and to add to that question, what's a minimum amount of light for a flower cycle that you think someone could get away with?
Yeah, I'll start there by saying I don't know, and I don't want to give bad advice. So I'm just gonna say I don't know what the minimum is.
Okay.
What I would say is, in terms of a general range, around 1,000 micromole, like you said, that's a great place to play. In general, we see a lot of commercial growers hovering around 1,200 these days. We see more and more growers creeping towards 1,500 micromoles. And then we have some growers, and this is kind of like the extreme outliers, but we have some growers that are doing up to 1,800 micromoles of top light, and they're exploring sub canopy lighting or under canopy lighting options or inter canopy lighting options, which I don't want to go down that tangent right now because I suspect we'll get to light distribution later in the conversation. But that's a really cool strategy for them, and it makes sense for them. But for the average grower, I would say between 1,000 and 1,500 is a good place to play. We're finding that most people are succeeding having good, healthy plants without too much drama. If you know what I mean, like not random, like why am I having foxtailing or revegging or some sort of weird morphology? Generally, in that range, people are okay as long as they have basic environmental management stuff going on. They can control their temperature and humidity, and of course, they are supplementing with CO2.
Since you brought up foxtailing and revegging, uh, how does light impact those particular effects, or this idea of newer white pistils uh, on a bud or flowering cycle? Because as I understood it, I thought revegging specifically was tied entirely 100% to photo period. Is that not
Yeah.
accurate, or are there other things around there to?
Um, from a literal standpoint, there are other ways to induce revegging, but from a
Hmm.
practical standpoint, it is it is primarily due to photoperiod. You're not wrong about that at all. Um, Things like foxtailing or any number of other sort of funky morphological things that you can get are largely down to light intensity. Um, and the exact mechanism we don't know again, and it pains me to say that because as you've heard from me before, I really like to get in the weeds and talk about all the kind of biochemical stuff going on, but we don't know. With foxtailing, what we've seen is that for folks that want to go with a higher light intensity, um, the instances of those sort of morphological outliers are lower when they're doing a more distributed light. And so by that I mean if they want to play at 1500 micromoles total, but maybe they're having some morphological issues when that's all top light, then if they take 300 micromoles of that or 500 micromoles of that and put it as intercanopy or subcanopy instead of all at the top, not only are they getting greater bud uniformity throughout the canopy and elevated bud grade, but they're also not running into a lot of those morphological issues they were having before.
Yeah, I've always thought of light over, let's just say 1200 ppfd as being a stressor. But I think as I'm saying this, that's probably not the best terminology. Maybe it's more of a trigger that just allows for less plant stress in general. As this thing's going so hard in terms of the amount of photosynthesis that's occurring due to the amount of light, it seems like to me um, it's much more open to stresses and other environmental triggers that can cause pretty significant morphological changes or other issues than I would normally see if I had been running at say 1000 or 900 ppfd.
Yeah, no, that's true. But another way to look at that, right, is I'm going to use an analogy of like how active a given human being is, right? Say you are somebody like me and you live a sort of like very average lifestyle where like you spend a lot of time sitting at a computer, you're walking around a lab, you exercise a moderate amount, but like it's a pretty kind of like middle of the road lifestyle, right? The difference between me and like an Olympic athlete, right, where they are training to be a sprinter or a high jumper or something like that, it's like they are performing physically at a much greater intensity and they can physically achieve much more than plant scientist Dave can. You know what I mean? But chances are they're a lot more likely to tear their ACL or roll their ankle or pull a muscle or something like that because they are operating at a really high intensity physically. Conversely, right, if someone has a totally stagnant life and they're living in a bubble and they do nothing, they're delicate in a different way. You know what I mean? So everyone ends up acclimating to their environment, whether it's a human, whether it's a plant, whether it's an athlete, whether it's somebody who doesn't do anything at all. Um, and something like, bringing it back to plants, if you're pushing them hard with highlight, you are getting plants that are like the Olympians, right? They're performing really, really well. But to your point, yeah, they're probably a little less robust to when a stressor comes along. And it's like I don't want to go on too big a tangent here, but we get a lot of feedback about living soils versus like a salt media kind of thing. And people say, well, salt is better for these reasons, or living media is better for these reasons. And what we tend to say is like, for commercial horticulture, we are pushing the plants hard. Excuse me, we're pushing the plants hard. It is like driving a race car, and we don't want to introduce variables that could be stressors favorably for the plants in certain circumstances, but in these circumstances, that's like a hyper controlled, really intense thing. We don't want to introduce any stressors that we don't really understand really well and know how they interact with light and everything else that we know we're putting in. Does that make sense?
Yeah, I mean, you're bringing up a broader issue with living soils in general in science, just in the fact
Yeah.
that there's so much variability. I mean, it's an issue across all soil science, I think, in general, but specifically in terms of cannabis research, most researchers don't want to do research in living soils because of the variability of those soils. It sort of it makes any replicability or conclusions that you might draw from it very challenging. So I understand why researchers want to do research with mineral salts in rock wool or cocoa, just a very inert substrate, because you can control and turn every single dial and keep everything the same across replicants. So I totally get that. Yeah.
Well, not to mention, the liability that it carries with it. If you're a company, like you're a technology provider, um, if you're a company that says, hey, use my substrate because it's going to do amazing things for your rooting or it's going to do amazing things for your yield. If you're providing living soils and you really can't control exactly what's in that substrate every single time and you're giving it to customers with an assurance that it's going to do something good for their crop, well, what do you do when 6 months later you got a bunch of customers that come back to you and say, hey, this isn't performing like the last batch? What gives? It's not that we're not interested in that kind of technology and living soils and stuff. And on a personal level, I actually believe in a more kind of like holistic system, including living soils. But that's not something that commercially I'm going to bring to a customer because I can't speak to it. I can't give them an assurance that it's going to be the same again and again and again.
Yeah, I think that because and this gets a little complicated. But as someone who works specifically on that side of the industry, what I do find is we are able to replicate things fairly consistency if we stay within certain agronomic principles in terms of fertility. Because yes, there are going to be differences on the biological side. Uh, that biology is constantly in flux. It's changing. It's not homogeneous. Soils are, and in soils, I'm including living soils, which are technically soilless media, are profoundly diverse and complicated and fascinating. And throughout all of those interactions, those microbial plant media interactions that are happening, what we're seeing from a very, very macro view is actually fairly consistent, I think. The plant really does control and balance those things. Now, can you screw it up? Absolutely. And it does happen. But as a general rule, I find it easier for a lot of, at least in commercial facilities, uh, more affordable because you're not constantly buying new media, and then also easier in a lot of ways because of the labor associated with it and the yeah, just the overall process. But that being said, it was interesting because I was at PhotoX and I was talking to I think almost everyone there was growing in mineral salts. A lot of the growers, at least I didn't talk to any specifically organic folks, but we're dealing with a lot of the same challenges. We had a lot of the same questions. It was a very collaborative conversation, even though we take different approaches on the on the fertility or media side. So
Well,
yeah.
and just to jump in there, I'm really glad you made that clarification because it probably wasn't a good analogy for me to make in terms of speaking to like substrates, for instance. Um, I'm not an expert in that, but from what you're describing, it sounds like there is quite a bit more opportunity there than I'd previously appreciated. And so, probably too big a conversation for us to dive into right now, but would love to learn more about that from you. And I'll probably just follow up with you after.
Yeah. The research just shows that a lot of the microbes that we're seeing in the soil are very similar, I guess, across the board. And we have pretty high levels of them. I mean, if the problem was that severe, every organic farm, because there's a lot of organic horticulture, agriculture being done, sorry, on scale right now, and we're not seeing massive crop failures due to these, small differences versus what's being grown in, greenhouses and under glass and using mineral salts. So I think there's more to it, but it is an interesting conversation. And I do hope that someday there could be more science around living soils. At the same time, I also recognize that like I don't know how much I could derive from that science. Like that's why I find the science that's currently being done with mineral salts probably more interesting because it is just one less variable that we're controlling for. But
Right.
anyway, let's get we could go
Sure.
down a big rabbit hole there. Let's get back to lighting, where You definitely are an expert.
Where I know where I'm talking about, what I'm talking about, at least a little
One
bit.
of the things that I heard at PhotoX this year that I wanted to highlight around light intensity before we move on to other lighting topics was that, and correct me if I'm wrong, light intensity increases did not cause any changes in THC or total cannabinoids. Now, on that note, can you say if the research showed anything around terpenes or other secondary metabolite production?
Hmm. Yeah. So I have to caveat this by saying that all of the research that I presented at PhotoX and that I'll talk about here, I always say at commercially relevant intensities. And by that, I mean the research that we've done from about, let's say, 1,000 micromoles up to 2,500 micromoles is the highest we've ever gone. And within that range, yeah, we don't really see a big difference in THCA, CBGA, CBDA, and all the other cannabinoids that we're quantifying. And in the case where we're working with cultivars that can produce cannabivirins, we're not seeing a huge swing in cannabivarin concentrations either. As for terpenes, it's the short answer is that we're not seeing clear trends. The longer answer is that we are seeing that as a matter of spectrum and intensity, we can manipulate certain terpene ratios. Normally, when I present this, I have graphics to kind of support what I'm about to say. But what I'll say here is that in the world of terpenes, right, you can group them in different families. There are monoterpenes that are based on 10 carbon chains. There's sesquiterpenes that are 15 carbon chains. There's triterpenes and tetraterpenes and so on that just have increasingly longer carbon tails, or not carbon tails, but carbon chains. And then within monoterpenes, there are things that are more like cyclic structured and things that are more linear structured. And the biochemical pathways that lead to these two branches, um, we can manipulate partitioning of these two pathways. Excuse me. So, we have seen instances where by manipulating white and red and far red, we can change, the ratios we get of cyclic versus linear monoterpenes, and we've manipulated ratios of monoterpenes and sesquiterpenes and things like that. And as someone whose PhD was in plant biochemistry, this is really exciting to me because I think, oh, okay, maybe there's a certain enzyme in this pathway that we're changing the activity of, or maybe there's a thing in the mevalonate or non-mevalonate pathway that we're manipulating. Because whether you get monoterpenes or sesquiterpenes or triterpenes or tetraterpenes, um, the precursors that make those compounds are called isoprenes. And whether you make your isoprenes in the plastids, like the chloroplast, or whether you make those isoprenes in the cytosol, which is just kind of the goop that all your cell
Mhm.
organelles just float around in. Whether you're making those isoprenes in the plastids of the cytosol determines or influences anyway what types of terpenes you're going to end up with. And so I think, oh wow, okay, that's actually really complicated. Then there are a lot of regulatory things that could be going on that change that partitioning. So when we see that light does play a role in this, it's it's inspiring. It inspires me to do more research and want to pursue it further. And I think, a lot of people at the end of the day are really, really interested in diverse chemistry, whether it's for a medicinal application or whether it's a psychoactive application, or even just you prefer one flavor or another. It's cool to see that we can manipulate this stuff with light. And I eagerly await for there to be greater market demand for things like that, because right now, um, we see things like that and we want to do more research on it, but research costs money. And analyzing a bunch of individual terpenes and other compounds costs a lot of money. And right now, no one is making lighting purchase decisions based on what can be done with terpene manipulation, which is a real shame. But if Fluence can't sell more lights because of something we discovered about terpenes, I therefore can't invest more money into that kind of research. You know what I mean?
Yeah, no, that makes sense. And it's a pretty broad research topic to try and tackle. Like that sounds like years or decades worth of work to really dial in. But what I'm hearing is the takeaway so far for just to catch growers up. And correct me if I'm wrong here, but essentially 1% more light is going to equal 1% more yield. Light intensity does not really change THC or total cannabinoids within commercial application ranges, normal ranges that we would grow this plant. And then we may light does impact terpenes, but we don't know exactly how that occurs and how to manipulate it to our advantage yet, especially as I think about this with the vast diversity of genetics that we have within cannabis already.
Yeah, exactly. Well said, and much more concisely said than me. So thank you for
Well,
that.
I just want to hit the highlights for folks because
Yeah.
this is a pretty complex topic. On that note, my thought immediately goes to the dilution effect. This idea that a plant has certain genetic potential, and we see this in other crops where as you grow more biomass, as you increase yield, I would assume that that THC would be more broadly spread across that biomass at a certain threshold. So, like the plant has the capability to produce genetically at its potential only so much THC
Hmm.
overall. And so, as we spread that over larger leaf surface, more bud sites, my overall THC levels could go down, but maybe that total cannabinoid content of that entire plant would stay the same. Do you want to kind of jump in on that?
Yeah, I would jump in simply to echo what you just said. A simple analogy is if you put a teaspoon of sugar in a water balloon and then you fill up that water balloon, that sugar is very diluted, right? Similarly, if you have a plant cell and it's got some THC in it and you just sort of dilute that THC in a bigger cell, or you have like this total quantity of THC that the plant as a whole can produce and you dilute it across a very big plant, yeah, it'll be less potent.
Yeah, and I don't know that we like because I know you've brought up the term like within a commercially applicable range. I think that there's a possibility that we haven't really hit that with cannabis in terms of THC and cannabinoids because I do see people growing very large plants with the same genetics and still having high THC levels. But this that doesn't change the fact that this concept doesn't exist already and is a factor that people should be considering as they grow plants. So I just want to throw out that caveat.
Yeah, actually, Tech, can I jump in on that? Because one thing that I'm really interested in is the research that's coming out of places like Wageningen University, excuse me, and they have research showing that certain wavelengths of light, like blue, like UV, like far red, at lower intensities, can significantly manipulate chemical profiles. That what we're seeing is that at higher light intensities, it really doesn't seem to do anything. And so I think about that, and I think, okay, well, there's a lot of potential if you're a grower that wants to kind of take like a low and slow approach, kind of like if you're smoking some meat, low and slow is the way to go. I think, oh, maybe you can do the same thing with cannabis. Play more like 4 to 500 micromoles and really dial in a chemical profile, whether that's with cannabinoids or terpenes, by using a really kind of specialized lighting recipe, right? And I don't have an answer for this right now. I'm literally just thinking aloud. This is something I'm really interested in, and I want to do more research on. I think I would encourage people to look into this research. But again, it doesn't seem to hold true at these really high light intensities that most growers want for maximizing their yield.
All right, you brought up spectrum. Let's just dive into spectrum.
All right.
Why not? So, can you start off by let's so spectrum's a range. Let's just start at the bottom of that range. Let's start in the UV blue area and talk a little bit about what it does, what the research shows, and maybe what's dispel some of the myths around the claims that we're seeing happening on these different wavelengths or spectrums.
Sure. And I'll keep this high level because I have a bad habit of getting really in the weeds about spectrum. But if you want me to dive deeper on something, please don't hesitate to ask. So, starting with, as you say, the shortwave light, we're talking about UVB and then UVA and then blue, right? In that order, they
So
go from shortest to longest. Go ahead.
let me pause you. Can we clump UV as one spectrum, or should do we need to talk about UVA and UVB as specifically different spectrums?
These are distinctly different spectrums.
Okay.
Yeah.
In
So,
terms of plant effect, I guess is the context.
yes. Yeah.
Okay.
Plant effect and the energy that these photons carry, and therefore also the health risks that these photons have. So maybe actually I should start with even higher energy photons or shorter wavelengths, and that's UVC. UVC light is a really amazing tool for certain applications in horticulture. It's around 254 nanometers. At least that's the UVC that's most commonly deployed. And this is very dangerous light in the sense that it has enough energy to break biochemical bonds, and that can give you a sunburn. It can hurt your eyes, like damage your eyes permanently, and it can give you cancer, right? So for a lot of reasons, you don't want to be exposed to UVC. Having said that, all of these negative effects that it has on your biological cells, it has those same effects on things like fungal spores and bacteria and other pathogens that you might not necessarily want on your plants. So you can strategically apply UVC to do like a surface sterilization of your crop. And this is broadly used in broader horticulture for like sterilizing strawberries, for instance, in a container. So really great technology, but obviously something you have to be very responsible with. And also you need to be mindful of the fact that you can't see it when it's on. It's not in the visible range of spectrum. So
Mm.
you might be exposed to UVC and have no idea, but then be very unwell after. So moving on from UVC, you then have UVB, which is less dangerous than UVC, but still dangerous. And it's not something that you want to be exposed to. And again, it's another wavelength of light. Um, usually when we're talking about UVB, we're talking about maybe 285 nanometers up to about 310 nanometers. It's still dangerous. You're still not going to see it, but it interacts with plants a little bit differently. Um, it interacts with certain cryptochromes, which are photoreceptors in plants. It also interacts with something called UVR8, which is a specialized UV receptor in plants. And um, it can, in certain cases, induce something called systemic acquired response, which is kind of like boosting the plant's immune system. It gives it a chronic stress where the plant just says, hey, I need to live a hardier lifestyle and be more robust to the environment. So that's really cool. Again, the research is, I would say, relatively sparse on UVB applications. And there are reasons for that. I mean, it is kind of dangerous. You don't want students doing it. The lighting technology is also not great. It's not something that you necessarily want to use LEDs for just yet because you can probably do better with fluorescent tubes. Um, and it's the lights all have kind of like a short lifespan, and for all these reasons, like there's a lack of research around UVB, and there's opportunity for a lot more, which is exciting. Suffice to say, we'll just move on to UVA. And UVA is nice because this is kind of like when you go to a 90s party and there's like a black light and everything glows, right? That's UVA. It's not terribly dangerous. Like you still wouldn't want to hang out in high intensity UVA for a long time or like shine it straight into your eyes and think that's a good idea. Um, but as far as like plant interactions go, it's going to be received by, again, cryptochromes. And I know I mentioned those already. Cryptochromes are a pretty broad family of photoreceptors. Like there's the Cry1, Cry2, Cry3, Cry4, and they absorb different wavelengths of light, but also they absorb differently at different light intensities. The thing about UVA is that, as far as I'm aware, a lot of the things that it does to plants can also be achieved with blue light, which for a lot of reasons you would just go with blue then. Blue is cheaper, it's a lot safer, it's going to have a much longer lifespan. So I'll just segue right into blue and say blue is a great tool for things like inducing compaction, right? The plants perceive blue as like, oh, I'm in sunlight, it's high noon, good photons are getting to me, I don't need to stretch to get into better light. So actually, they'll become a little bit more compact. Um,
When you say more compact, I assume you're talking about internode spacing.
yes, sir.
Does it also impact leaf morphology?
Yep. Yep. So with blue light, you will generally speaking have thicker leaves. You will produce more callus on the leaves, which is like kind of like the waxy. I'm sorry, callus isn't the right word. Cuticle is the word I'm looking for.
Cuticle.
So like the waxy film that's on surface of leaves to protect themselves from various environmental stresses. And in general, you'll also have more pigmentation in the leaves, so richer chlorophyll content versus if you just have like a white or a red light.
Now let me back up a little bit because I have some notes here that I took.
Hmm.
Um, the notes that I took from PhotoX said that, and correct me on this too, 3.5 hours of UVB decreased THC levels. Is that in the research that was presented? And I'm not sure if it was by you or someone else. Do you know what I'm talking about there?
I don't know specifically what you're talking about, but I can generalize around the research that we have done on UVB, as well as the research on UVB that I'm aware of from Dr. Bruce Bugby at Utah State, as well as Dr. Yubin Zhang at the University of Guelph.
Yeah. What are the effects of UV generalized in terms of yield, cannabinoid content, and terpene production?
Yeah. So in general, according to all of the kind of like modern UVB research on cannabis, basically any amount of UVB is bad. And the more UVB that you apply, whether you apply it through a higher intensity or flux density, or whether you apply an equal intensity but for a longer duration, the more UVB you apply, the worse it is for the plants. So yield goes down, potency goes down. The plants look very, very stressed out. We see the leaves canoeing, if you know what I mean. They kind of roll up and then they'll also curl in on themselves.
Hmm.
It, you know, not to anthropomorphize, but it seems like they're really trying to just get away from the photons and protect themselves. So, for the time being, we don't see any commercially beneficial application of UVB. That's not to say that we don't think there could be one, but the research that we've all done, and by we I mean Fluence, I mean Dr. Bugby, Dr. Zhang, we've all taken the approach of applying UVB during flower development in hopes that it's going to do something good for cannabinoid biosynthesis. I think that there's opportunity maybe for UVB applied earlier in development, like late prop or early veg, with this idea that, again, maybe if we kind of like chronically harden the plants to UVB, maybe that will give some kind of downstream benefit, but we don't know yet.
Hmm. Are there any claims being made in the market right now around UV that are, because it sounds like, from what I'm understanding, UV light is uh, not very efficient. Like it takes a lot more electricity to produce it versus these other spectrums, and it's potentially dangerous for humans, and it doesn't seem to increase cannabinoid production. Are there any claims right now out there that you're aware of around UV that people should be cautious of, maybe?
Yeah, again, I think that you've nailed the risks and kind of the negatives of UVB, but the claims are out there that UVB will enhance secondary metabolism. And again, it's one of those things that we simply haven't seen it. So the companies that have done research on this or are familiar with research are less likely to make these claims, I think. I've also heard a claim that UV photons help draw PAR photons or photons in the range of photosynthetically active radiation. Uh, the claim is that UV can help somehow draw those photons deeper into the canopy, and therefore you have more light penetration, which theoretically means more overall photosynthesis, which theoretically means more overall yield. That claim strikes me as particularly odd simply because photons don't interact with each other that way. And UV also, as a shortwave photon, bumps into a lot of things and is reflected from things. It certainly does not penetrate deep into a canopy. So I think it's a claim that sounds sort of exciting, but in reality is not something that growers should be taking too seriously.
I think there was another claim that I heard around UV and insect protection or insect deterrence. I don't remember exactly what it was, but I believe there was some effect on insects from UV, but it was not replicated in commercial applications. It was just one study that was done. So I think there was some caution around that. Suzanne was talking to me about it, and
Oh,
I
cool.
don't want to misspeak, but I think there was something around there too. You brought up, and I didn't even have this on the list of topics, but I think it's interesting. You brought up light penetration
Hmm.
because I've heard people say, my light penetrates further into the canopy than light B or competitor light. How how does that work? Because I that that got me into a conversation on this concept of the inverse square law, which I think is really interesting. I know you and I touched on it off air.
Right.
How does that apply to horticulture and these conversations?
Yeah. So light penetration, I'm also very interested in this. Fluence, we used to say that white light worked so well for cannabis because of light penetration, as opposed to something that's a more predominantly pink or a blurple type, like red blue light. And we had said, well, for a couple of reasons, you're penetrating deeper. You're not having all of your photons immediately absorbed by superficial leaves, and those green photons that will get absorbed by leaves, but then retransmitted as longer photons, those will be more photosynthetically productive deeper in the canopy. These are all cool sounding nuggets of information that are actually somewhat supported in the academic literature. And there's really, really like cool papers that show light measurements at different depths in canopy and even within a given leaf. They'll say, for a given leaf with certain um, light qualities, all of the photosynthesis is occurring on like the first couple layers of cells, whereas with a more with a more white light, you're getting deeper penetration and driving more photosynthesis deeper in the leaf. And again, like that is factually true. In isolation, a single leaf will photosynthesize deeper in its leaf with a more white light. At least that's what the science tells us. Now, in practice, what we are finding is that we could be talking right now about cannabis or tomato or cucumber, really any crop where you have like a really dense leafy canopy where it's really shaded as you go down through that canopy. What we're finding is that white actually isn't penetrating all that much better than something that's like 80% red and otherwise white, right? And I call that spectrum out specifically because that type of spectral mix that looks pink to the eye but is roughly 80% red and the rest is just background white, that penetrates pretty well too. And having something that looks white to our eyes, it's not really benefiting the crop in that way, unfortunately.
So I have a very low level understanding of how this all works. And I think it's really interesting because the way I understand this, so let me back up. The inverse square law, I'm just going to state it. It's a mathematical concept that intensity is inversely proportional to the square of the distance. What does that mean? That's not very useful for the average grower. Essentially, in close distances from that light, as you move further away, these photons are going out, and as I understand, they're essentially spreading out. They're hitting less leaves directly right below the light. And
Mhm.
as you move further away from the light, it's going to drop off more dramatically. So like the example in the article I'm looking at here, it's like moving from 1 meter to 2 meters away, you're going to lose 75% of your light. But if you're way far away, 4 to 10 meters, that light intensity may only change by 5%. So as we bring our lights closer to our canopy, we're going to have and I see this with my light meter, we're going to have a greater drop off as we move away because in my head, what I'm picturing is all these photons are shooting out of the lights. They're hitting off of all of these different things, whether it be the wall, the leaf, all these things, and then shooting around until they're being absorbed by the plant. How does this all really apply horticulturally? Like, how do we maximize this? Because I assume if I have a tight canopy and that light is hitting that canopy, there really isn't potential for penetration. Like when I stick my light meter down below there, the photons just can't get through there. And
Mhm.
so they have to be reflected off of something, or they have to hit a leaf that's already maximized its photosynthetic potential. And it's really just, I assume, then just bouncing off at that point. It's not being absorbed. How
Yeah,
how how wrong am I in all of this in the way I'm describing it?
you're not. And Tad, you're very humble. I think you got to give yourself more credit because you have it right on pretty much all these things. So the way that I kind of think about the inverse square law and try to make sense of it is like if I go outside and I'm standing on the road and I think, oh yeah, it's basically this bright outside and I'm feeling this much radiant light and radiant heat from the sun. I don't think it's going to change a whole lot if I go up on the roof instead, right? I've technically gotten slightly closer to the sun,
Mhm.
but my perception at that point is not good enough that I'm going to know the difference between how the sun feels and looks from my roof versus the road, right? Because we're so far away from that light source that that is a trivial distance that I've changed from the road to the top of the roof. To go kind of the opposite and put this in horticulture terms, I'm going to give the example of people that are growing in multi-tier applications because in multi-tier, people tend to have the plants much closer to lights versus if they're doing like a single tier kind of high bay solution. So this is something that people do need to be aware of if they're doing plants that they know they want to grow in, let's just say 1,000 micromoles of light, right? It's like, well, okay, what do you mean by that? Do you mean 1,000 micromoles when they're at their full height, or do you mean 1,000 micromoles the whole time during their development, or something in between. And sometimes people get not upset, but a little confused why they're not having the crop perform as expected. Um, and it's because their plant spacing relative to that light isn't quite right. And really, if they say, for instance, I want to have 1,000 micromoles on the crop the whole time, even when my plants are 10 inches tall versus 36 inches tall, it's like, okay, you can achieve that, but you're going to need to manipulate your light intensity throughout the plant development so that at top of canopy, you are hitting that 1,000 micromoles per meter squared per second. Conversely, if you have your light configured such that it's really intense down here when the plant is young and short, and then you let that plant grow up to the point where it's only a few inches away from the light, you got to be really careful that you don't just end up cooking your plants
Mhm.
because the light intensity is going to be much, much greater close to the light like that.
Yeah, when I measure light intensity, I'm sure you're doing it much more carefully. But as a grower, going around with a par meter or even a photon, device, something that measures light, I kind of just quickly throw my light into different places or my meter different places under the light to get kind of a rough average that I calculate in my head and say, okay, here's my highest bud, here's my lowest bud. My canopy's fairly even. What am I getting at the edge? What am I getting directly in the middle? And I make sure that that is approximately around whatever my target par levels are. Is that a good approach, or is there a better way I should be doing that? Because we're talking about this like 1,000 PPFD is evenly hitting our canopy.
Mhm.
And as you know, that's just not the case. There's going to be spots that are 600, 700. There's going to be spots that might be 1,200. What's the best way to average that or figure it out?
I think what you described makes a lot of sense. And then how particular you want to be with the light measurement and light mapping depends on the scale of the facility. So, for instance, if you have a large room and you have a lot of lights above the plant, particularly if those lights have some optics that help light spread, you can expect a pretty good uniformity across the top of that canopy, right? And you can work with your lighting provider to develop a light design specifically using their light models. So, like in the case of Fluence, right, we have Raptor and we have Spider and we have Viper and so on. And depending on the grower's objectives, right, we can manipulate the light design and the number of lights that they use and even the platform of light they use to manipulate uniformity. Some growers say, I need to have a uniformity of 80% or better at any cost. And we'll say, okay, well, you can go a couple ways, right? You can increase the number of lights over the canopy so that you have like a lot of overlap between the lights, and you do get a really great homogeneous light environment across the space. Other growers say, yeah, that's really not so important. Um, you can reduce the number of lights. You can probably use a slightly different platform, thinking about like Viper versus Raptor in the case of Fluence. But for somebody that maybe has a smaller space, right? Smaller spaces are always harder to make more uniform. And I'm not just talking about lighting. It's harder with climate
Mhm.
and nutrition and everything else. So I think the best thing that you can do is for a small space, manage reflections, right? I mean, I realize this maybe isn't entirely what you're asking, but still, I would tell someone,
Well,
go ahead.
well, let me add on to my question
Sure.
then, because the other thing I have is like these photons that are not hitting my plant. So as we move the light further away from the plant,
Hmm.
there's less photons hitting the leaf directly below the light. All right, that's why my PPFD goes from, and let's just say 600 to 1,000, depending on how far away the light is from the canopy. Now, my question is, because you brought up reflectivity, that was my next question, was like those photons are not losing energy per se. They're just not being directed as precisely straight down as I understand. They're like going off and hitting other things and reflecting and coming back. How much light loss am I really getting from an energy perspective? In terms of electricity I have to produce. If I have my lights 5 feet up using like a high bay greenhouse light versus these, bar lights, am I really losing the light if it's just like bouncing around in a given room with white walls and other plants, or what? Because the photons aren't losing energy, right? They're just cruising around until they hit something.
Yeah. So again, I hate to say it, but it's another complicated answer. Um, energy can't be lost, right? It can only be converted. So if a photon doesn't make it to a plant immediately, then it will go to the wall, and depending on the paint you use and the material of the wall and so on, you'll have uh, a coefficient of utilization that describes how efficiently all your photons are getting to the plant and becoming more plant basically.
Hmm.
Uh, you can have a coefficient of utilization that corresponds to materials and colors as well. If you have nice, smooth, reflective walls that are painted white and have like a glossy paint and so on, then you can expect that that energy will make it to the plant eventually. But you will lose something along the way. Like some energy will be transformed to heat when it hits the wall. And then even when those photons get to the plant, it's not like 100% of that photon energy is converted to plant biomass, right? That energy can either go into photochemistry, which is what you want, or it can fluoresce. In other words, it can cause a biochemical kind of interaction with the plant such that the photon is re-emitted as a slightly longer wavelength,
Hmm.
or it can just produce waste heat, and you can end up warming up the plant. So again, I know it's a little bit of a technical answer, but the short answer is that um, if you have a good reflective environment and you have the plants and the lights situated in such a way where you've made some effort to capture as many photons as you can, it's not that wasteful at the end of the day. You're not losing a lot of energy to waste heat and things like that. But I mean,
Okay, that's
there's
good to
so many
hear.
caveats. Yeah,
Yeah, that was. It's just something I've wondered about because I always want to be efficient with my light and electrical use. So that's good to hear that it at least is getting there eventually, or mostly reflecting. Um, all right, we jumped around a little bit. We got off topic. We were talking spectrum. We were kind of in the blue range. I want to get back to that. So
sure.
we've already established that red is more efficient. It uses less electricity. The plants can absorb it. Why? But blue, as you described it, will give us tighter internodal spacing, larger leaves, maybe some protection on the leaf through the cuticle production. Why do we want blue in our light? Why not just go fully to, you know, red longer wave spectrums?
Yeah. Well, if you were to exclusively use red, um, the plants would be very leggy or etiolated or stretched, is the simplest way to say that.
Hmm.
You'd have really long petioles, which are like leaf stems. You'd have really long internodes. You'd have thin leaves. The leaves would look chlorotic or pale. Generally, you just have very unhappy looking plants. And I haven't even brought up the topic of photobleaching yet, but suffice to say, all of the buds that you develop, um, they might put on sufficient mass, and the chemistry, as far as cannabinoids and terpenes, might not be terribly affected, but they'll look really bad. They'll be really sort of off white in color, which generally doesn't fetch a very high value on the store shelf. So, to get back to the point of why have some blue, I guess the simplest way to say is that just it brings balance. But the truth is that you probably don't want distinct or discrete blue diodes most of the time, or at least you don't have to have them. You can get sufficient blue just through a white diode, and that's going to do what you need to keep the plants from looking really, really weird.
So in your presentation, you mentioned, I'm looking at one of the slides that you
Okay.
presented. You say at commercial intensities, blue seems to have no significant effect on yield or cannabinoid and terpene concentrations, with surprisingly little effect on morphology. Can you kind of reference that in terms of what you were, how that fits with what you're sharing right now,
Hmm.
and how those two are not mutually inexclusive?
Yes, for sure. So, um, when I talk about commercially relevant intensities, again, I'm talking between 1,000 micromoles and about 1,500 micromoles. And a lot of the opportunity to kind of turn the biochemical knobs up or down within the plant at those intensities, everything's already set to 11. You know what I mean? Like you can't turn the knob up anymore. And so the plant is just driving all biochemical pathways as hard as it can. It's consuming its internal resources to make all of the compounds it thinks are most essential for that situation. And so a lot of the manipulation of biochemical pathways that you might be able to do with blue light at lower intensities are basically overridden at that point. The plant just can't do it. Now, in our research, we're always looking at three or four things, right? There's always the pillar of yield, there's the pillar of morphology, the pillar of chemistry, and the pillar of economics. And what we saw was that, okay, blue is not really affecting yield, but we didn't really expect it to. That's not blue's job. Blue's job is theoretically to manipulate morphology and occasionally chemistry. So again, we applied blue in a few different ways. We tried having more blue during vegetative development. In that case, the research was done around 600 micromoles per meter square per second. And we also tried having different applications of blue during flower, whether as a part of the total spectrum or whether deploying blue at like the end of the cycle or something like that. And again, it just didn't really do very much. Honestly, we expected blue to be pretty impactful when applied during vegetative development. We expected to have tighter internodal spacing as compared to a spectrum that was more pink or more just like white. And it's not that it didn't do anything, it's just that it did a trivial amount of compaction. We had a difference in our canopy height of, 1 or 2 centimeters. And we said, well, this is statistically significant. In terms of reliability, in terms of our data collection, this is a thing. This just probably isn't going to matter to anyone. And so that's why we say, okay, well, the impact of blue in this particular scenario really is not so pronounced, not so pronounced that we're going to worry about it. Excuse me a minute.
So, yeah. So what I'm hearing you say essentially is, yes, we need blue in there for certain pathways, metabolic pathways. We don't want a purely red light for that reason. And it doesn't, however, at the light intensities that we're applying it, we're not getting dramatic impacts on the plant, essentially. Um, and I'm saying this kind of funny because I don't want to steal your thunder. As we move into red, which I think is some of the more exciting research that you've done recently around photobleaching. Can we go ahead and jump up into the red spectrum and talk about that now and what your findings were?
Definitely. So, in terms of our research, we have focused the majority of our research around red light for the last 2.5 to 3 years. And that's because of what you just said. Red photons induce a thing that we've called photobleaching. Our sister company, Philips, they've been calling it white tips for a little while. And I think either name is fine because the like root cause and what's going on, we don't know. And Philips doesn't know, and like there's basically nobody knows. We've had theories,
Now,
and go
yeah,
ahead.
I don't want you to go into it because it'll take you 2 minutes or 3 minutes to say it all out. And it was way over my head. But essentially, you listed these hypotheses that were like highly complex metabolic pathways and interactions. I don't even know if I'm using the right terms to describe what you were sharing, but I remember thinking, "Holy cow, this is crazy." Uh, the fact that we don't understand it and the fact that it's so complicated. Do you want to give us a shorter, like 20-second
Yeah,
inference on what you think
absolutely.
it might be?
Yeah. The short version is that chlorophyll is what makes plants green. And we thought that because chlorophyll is so good at absorbing red, if you use too much red, then it becomes unstable and falls apart. That's the short version. A slightly longer version is we thought that we could help this by adding far red, and adding far red only made things worse. It made chlorophyll seemingly more unstable, or maybe I should just say it made the instances of photobleaching more frequent and more severe.
Okay, so the big issue with photo bleaching is that people just don't like the way it looks, right? I mean,
Right.
it's it's happening specifically to the bud itself. The bracts are getting turning like a whitish color almost. They're literally losing all their chlorophyll, and it makes it harder to sell the flower. But that doesn't impact, as I understand it, the cannabinoid content or any other issue associated with that flower. Like it's still a perfectly good flower. It's just unsightly. Is that
That's right.
accurate?
That's exactly right. And we've actually seen instances with some cultivars where we have higher cannabinoid concentrations in the photobleached bud than unbleached bud.
Oh, that's fascinating. Okay. Hmm.
Yeah, so I don't talk about that too much, not because it's a secret or anything like that. I mean, I'm talking about it here. I don't talk about it much because, again, those are the outliers. And so a lot of what I try to present and communicate are the generalized trends that we see in terms of how light interacts with cannabis. And I don't want people to make a lighting decision thinking that, they're going to use a really high red thing and induce bleaching and then get really potent bud and then not experience that when, again, that really only is true in one or two kind of unusual cultivars.
So this is off the top of my head, but knowing that, so let's say assuming no changes in secondary metabolites and cannabinoids, as a home grower, if I don't care about the look of my bud, could I, in theory, run a much higher light intensity, knowing that I'm probably going to get some photo bleaching? But again, if this is just for my own personal grow, why wouldn't I want to do that, knowing that 1% more light equals 1% more yield ish? You
Yeah,
know?
do that. It's a good idea.
Okay. Okay. So, provided we're okay with photo bleaching, we could be increasing our yields while not sacrificing cannabinoids, which is ultimately and terpenes and other secondary metabolites, the whole reason we're growing this plant.
Hmm.
That's fascinating. Okay. Cool. So, getting back to the red stuff. So, the reason we use red, as I understand, is because it's more efficient, it's cheap to produce. So we're getting the best bang for our buck in a light, and it seems to work as well as other, white light and other spectrums. We saw it with HPS for decades. Um, what, but the risk with red, as you stated, is photo bleaching is more likely to occur. Can you quantify that for listeners based on your research?
Uh, I can try. It's difficult to quantify. I mean, what I would say is, first of all, the quantity of red photons that induces photobleaching is about 500 micromoles per meter square per second. That's the PPFD of just red. Plus or minus about 100 micromoles on either side. So, said differently, between about 400 and 600 micromoles of red is where you're really in that danger zone. And, um, there are some cultivars, like off the top of my head, White Rhino or Blank Check. We work with one at our research site called TXOG that, they're going to bleach no matter what. It doesn't matter if you're using LED, it doesn't matter if you're using a lot of red. It doesn't matter if it's a Tuesday. You know what I mean? Like they're going to bleach. So what we say is that it seems like about 20% ish of the cultivars that are commonly grown in the commercial space these days are what we would consider to be on that more sensitive side of the normal distribution. And then there's, an equal number, let's say 20% of cultivars out there that are very red tolerant. For instance, the Kimavara of San Fernando Valley that we've worked with in our research, we can just use a really high, like 80% red light the whole time, and it doesn't bleach. So that's why, again, not that this is not a commercial or a sales pitch or anything, but I'm just saying this because I work at Fluence and I'm aware of the product. We have a tool now. It's a platform called Raptor 2 Top Light, and it has a spectrum we sell now called T48. T means tunable, and then the 4 and the 8 mean that it ranges between 40 and 80% red. And it's an awesome tool because you can deploy this one light, and then depending on the cultivars that you're working with, you can dial in the amount of red up or down and then overcome photo bleaching. Or if you're growing for extraction or you otherwise don't care about photo bleaching, you can just use really high red the whole time, bleach the plant, but have great efficacy and really high PPFD.
So many questions. So as we dive into red here, I guess my question on the photo bleaching is, as a grower, just with a, let's just say, a very standard commercially available white light LED, what is the approximate percentage of red? Like if I wanted to calculate out, okay, how do I stay under 500 ppfd? What's the white light range to avoid? Like, how high can I go without having a way of measuring red specifically and assuming across a variety of different white lights on the
Sure.
market?
So Fluence's BW4 spectrum is 41% red, right? And there's an engineering tolerance within that, so it's like 41% red plus or minus like 1.5 or something like that. Uh, but a lot of the white lights on the market have tried to emulate that, and our eyes will perceive a light as whitish and not very red up until I don't know, let's say maybe 65% red. So obviously, of course, I can't speak to every light out there and every manufacturer and so on, but at least at Fluence, we say, okay, well, really everything between 40 and 60 in the common vernacular, we talk about that as like a white-ish light.
Mm-hmm.
Um, but in terms of like photo bleaching avoidance and kind of like risk avoidance, I would say, look, when people are buying a light, hopefully it's a light designed for horticulture. Even if it's a small home grow or something like that, hopefully you're still buying a light where you can get the spectral information and they'll say like, well, here are the RGB values of 41, 41, 18 is ours, for instance. And then you can just calculate like, okay, if I'm putting 1,000 micromoles of light on my crop and it says that it's 41% red, 41% of 1,000 is 410 micromoles. So it can be a pretty simple calculation. But again, if you don't have that information, you can go down the rabbit hole if you want to. You can get a spectrometer and actually literally take that measurement yourself and then do the calculation. But if you don't want to do that, then I would probably just start with an assumption that it's roughly a third of the light you're seeing. I mean, it's a kind of an impossible question to answer, but sunlight,
So,
one third of that is red, right? So I'd start there with my base calculation.
so potentially, let's just say 1,000 to 1,200 is a very generalized range based off the
Sure.
numbers you're sharing with me. Does that sound reasonable? Maybe even it's a little higher than that
In terms of like total photon flux,
in terms of potential, yeah, potential risk of photo bleaching. If we're giving the plant that over a 12-hour
oh,
period.
okay. I think I see what you're saying. So if you have a like a white light
Yeah, like if
and
I just walked in my grow room,
yeah,
didn't tell you what white light LED I was running in there, just a broad spectrum horticulture light, what levels would I have to be like, okay, now I'm getting up into a range where I might have to be concerned about photo bleaching. That was sort of what I was getting at.
I see. Okay, yeah, thanks for the clarification. Um, I would start to be thinking about it as I exceed about 1,200 micromoles, but it gets really complicated and really interesting after that. If you don't mind, I'll share a story here, which is that in our early light intensity research, and this is back, I guess this study I'm thinking of was in 2021, we went all the way up to 2,500 micromoles of top light. It's like a stupid amount of light. We walk in the room and the ceiling was just lights, and we had to move a bunch of electricity around in the building to do the study and so on. Like not commercially feasible at all, but we wanted to see what would make the plants break. In that study, we used the BW4 spectrum, and we were working with Blue Dream, and we might have been working with a cultivar called Blue Bonnet and Skunk as well, but I can't remember. We definitely have Blue Dream. Anyway, the point is, of those three cultivars, none of them bleached. And the thing is, according to the math and the generalizations I just said, if you calculate how much red was in that, I don't know if actually off the top of my head, 41% of 2,500 is whatever. It's a number that is much higher than 500 or 600 micromoles, and therefore it passes that threshold where we would say photobleaching would happen. So what that says to me is that, you know, whether or not you're going to photo bleach is not exclusively dictated by the amount of red in the spectrum, right? There are clearly other things going on, and we don't know what those other things are yet. What we do know is that the peak red wavelength does seem to matter. Have you seen or heard anything about like 660 nanometer red versus 640 versus 630?
No, no, I just as a grower, I think you generally just hear red and blue, and you don't. I mean, I'm sure there's growers that dive into it, but no, I haven't heard about specific peaks.
Yeah. Well, and I mean, to be fair, right? Just hearing about red or green or blue, most of the time that's fine, you know. But if you're a lighting company and you're a lighting researcher like I am and like my team is, we worry about these things. And we hear diode manufacturers make claims about what their diode does, right? Because Fluence isn't a diode manufacturer. We use diodes from other suppliers and we combine them in ways that we think are going to be good for the plants. But you know,
And let's be clear, I think that's what pretty much everybody does for the
that's
most
right.
part. As a
Yeah.
generalization, um, yeah, I just want to throw that out there for listeners.
Yeah. And thanks for doing that. So, when we're talking to diode suppliers, they make claims about what certain diodes and wavelengths and so on can do. And some of them have actually pretty legit research programs. So that's cool to see. But there's been kind of like some noise recently around the idea of using, instead of 660 nanometer red, which is what's common in horticulture, using instead like a 630 or 640 nanometer red. Or maybe instead of replacing that 60, uh, using 660 plus something like a 630 or 640. It's again, I realize this is kind of in the weeds, but we think about this and we think, oh, maybe this is an opportunity to overcome photobleaching while using more red, right? This is really exciting for us. But then we look at Wageningen University, which for listeners that might not know, Wageningen is in the Netherlands and it's considered the foremost sort of center of excellence for horticulture research in the world. Um, they're still learning their way around cultivating cannabis, but in terms of lighting research, they certainly know what they're doing. They did a study comparing a few different spectra with either like a single red peak at 660 nanometers or what I describe as a dispersed red peak. So they had a 660 and a 630. And again, really, really exciting because I'm thinking, oh, great, they're spreading out the energy. This is going to be less stressful on chlorophyll. This is going to prevent photobleaching. It was the opposite. The one treatment they had where they had dispersed red peaks was the only treatment in this study that actually did induce photobleaching in cannabis.
Oh,
So
that's
again,
really interesting.
it's
Yeah.
really interesting and it's counterintuitive and it's a little discouraging, right? This is the nature of being in science. You can spend your career studying one thing and you think that you have an understanding of it and you've done more research on this thing than anybody else in the world. Like that's how I feel about photobleaching. I think I know this. I get this more than anybody else. And I don't say that egotistically, just I've spent a lot of time on it. And
Yeah.
then you see a study like this come out and it completely contradicts what you think about how it works. Right. And you just have to accept it. It's like, okay, look, I can't dispute the way they did this study. It seems reasonable. And I think, more studies on this are worthwhile, but I have no choice but to question my own understanding of the mechanisms here and throw out a lot of the assumptions I've made. So anyway, more on
See,
that
I would
later.
take the opposite approach to that. I think that is really exciting that they found that result because it speaks to science in general. And as a citizen scientist myself, I love the idea that science is, I guess, open-minded, like it's constantly evolving and changing, and even it's agnostic to our assumptions and our beliefs. And so when we get something that dramatically challenges our worldview, uh, I think that's exciting.
Yeah,
I like that. But I
agreed.
do hear
And
you. It's frustrating too because you think you have something figured out, and then we learn more, and that science changes and evolves, and I think that's amazing.
I'm there with you. It's frustrating in an exciting way. So don't get me wrong. I mean, this is a cool discovery. And, some people would say it's a failed experiment where it's like, oh, well, you didn't get the outcome that you hoped for. It's like, no, no, no. It's still a good experiment. It's still a success. It's just kind of a bummer that it didn't do what we wanted it to do. And for us, we kind
That's
of,
why we have to do these things though. Like
yeah,
you see these experiments and you're like, oh, alcohol is bad for you. They just confirm that. And you're like, duh, we knew that. Or smoking or something causes cancer, right? But without that research, there's always that chance that we think we have something understood and we don't. And so we're always learning. But yeah, I hear you. That's
yeah,
great.
yeah. And we
Um,
experienced the same thing with far red, by the way, when we thought that far red was going to help overcome photo bleaching.
let's talk about it. So
Sure.
I do want that's a great segue. Let's dive into so we kind of covered red and photo bleaching. Let's talk about far red. Do we want far red in our lights? What's it do? What are the claims?
Yeah.
Yeah.
Again, the short answer is probably not at commercial scale yet. And it's a bummer to always say, well, you don't want this, you don't want this, you don't want this. It would be way more fun if I could say, yeah, blue, use it this way and you're going to get some kind of cool result. Use far red this way, you're going to get some kind of cool result. But the reality is that these things aren't delivering on what we expect them to deliver. And in the case of far red, what we expected was that we might be able to do things, for instance, like really manipulate morphology in general, right? Far red is expected to induce stretch, longer internodal spacing, greater leaf area, albeit with thinner leaves, slightly different leaf architecture, things like that. And we were seeing a little bit of that, just like how we saw like a little bit of blue compaction response, but it wasn't nearly as profound as what we see in things like lettuce or strawberry or in vine crops. So then we say, okay, well, not that. Could far red be useful for driving yield somehow? And there's discussion of things like the Emerson enhancement effect, which we can get into if you like. But
I
generally,
want to, but
okay,
before you do, I just want to ask you a question. So this seems to support a concept as I understood it from Dr. Bugby, this idea that light intensity is more important. It's still a more important mechanism than spectrum. Is that still a fair statement? Like
yes.
giving the plant more light is going to increase your yields and is more important than necessarily like hitting a very particular spectrum of light.
Yes, with the usual caveats, right? Like if you give a plant 800 micromoles of red light, that's going to drive photosynthesis much better than 800 micromoles of green light, for example. But
Yeah.
within reason, yes, that is a very good and fair statement.
Okay, so then let's dive into the Emerson effect because I had to look that up. You when you started talking about, it, I was like, I have never even heard of this, but then I realized it's a pretty commonly talked about concept within the horticulture world and lighting in general. What is it? What is the Emerson effect?
Yeah. So the common interpretation of the Emerson effect is that if you use a combination of far red light and par light, so light between 400 and 700 nanometers, then you will get a net photosynthetic rate greater than the sum of its parts. Said differently, that's basically implying like, hey, far red by itself might not drive photosynthesis very well, and par might drive photosynthesis okay, but if you put them together, you get some kind of amazing photosynthetic rate. Now,
Yes. So the sum of the two is greater than their individual parts.
yeah,
And what does the research show on this? Because it looks like I'm cheating. I'm looking at a page describing it. It looks like Dr. Bugby, as well as a gentleman by the name of Paul Kusama, has done research at Utah State on this Emerson effect.
yeah, and I would add Shuyang Zen to that list as well.
Okay.
Paul Kasuma and Shuyang were working in Bruce's lab, um, kind of in the late 20 teens and into the early 2020s, I think. Paul is over at Wageningen now, and Shuyang is at Texas A&M, by the way, if anyone's curious what's become of them. Anyway, yeah, so they look, it's tricky because I'm not intimately familiar with all the research they've done. So I think maybe I won't speak to it other than to say a lot of the conversation that came out of that research group was around the idea of EPAR, which is a slightly different thing than the Emerson effect. So I think what I'll do is I'll speak to the research that we've done at Fluence and what we've seen as it pertains to cannabis. And what we've seen was that when we have light treatments where we compare a total photon flux between, let's say, 400 nanometers all the way up to maybe 850 nanometers, so a range that includes far red, right? When we compare that versus an equivalent total flux, but only with photons between 400 and 700 nanometers, then the net photosynthetic response and net yield response that we get is equal. Does that make sense?
Yeah. So when you do two trials, one that includes far red and one that just excludes it, or you know, only goes up to red, you got pretty much the exact same response from the plant. So
Mm.
if that is the case, wouldn't having that far red in there be good because it's a more efficient light waveform?
Yeah, so that is a great point in theory. So you're saying that because far red is a longer wavelength than red, right? And theoretically, it's less.
As we move that direction towards red, as I'm
That's right.
understanding from our conversation, everything becomes more efficient and cheaper. And yeah, is that
Yes,
not the case with far
you are
red?
exactly right in terms of the theory of how LED technology should work. In
Okay.
practice, there's also the reality, which is that red LEDs are much more commonly used in a lot of different technologies. Um, Therefore, the fundamental technology of red diodes themselves is much further along than far red diodes. So even
Okay.
though you are theoretically correct, far red photons are lower energy than red photons and therefore should be cheaper to produce. In practice, red photons right now are much cheaper to produce than far red photons.
Okay, so it's going to cost more to make a light with far red than one without.
Yep,
Essentially, what you're getting at.
that's right. Yeah.
Okay, which offsets the amount of electrical savings I assume we would have over the given lifetime of a light.
Yeah. Well, so the far red diodes are going to be more expensive to purchase. Um, they're also going to be more expensive to operate. So basically, just more expensive in every way.
Why is that the case in terms of operational costs? Because I thought as we moved red, things were getting cheaper operationally.
Yeah. Sorry if I wasn't clear in that explanation. So again, you are correct in the theory of how LED technology should work, but again, the sort of technological advancements that have happened with red diodes is
Okay.
just much further along than the diode providers and the diode producers. Uh, they just haven't done as much R&D in making good far red diodes, so they're less efficient currently than red diodes.
Ah, okay. That explains it. That makes sense to me then. Um, so you say the Emerson effect isn't relevant at commercial PPFDs. This idea that far red and red combined produce greater than the sum of their parts. You're specifically talking about the range from 1,000 to 1,500 ppfd.
Yes. So to explain this, I am going to have to get pretty technical in how the light reactions of photosynthesis work, and this is a little bit difficult to hear without a visual aid. So I'll do my best to explain this clearly.
Okay.
But you know, no one should feel discouraged if they don't follow this, and they can just blame me for not explaining it well. So in the light reactions of photosynthesis, there are two big protein complexes called photosystem 2 and photosystem 1. And I'm going to skip a lot of the steps in between these things because they don't really matter for this conversation. Basically, the first step in photosynthesis is that light is absorbed by photosystem 2, right? And that can be a bunch of different wavelengths of light, basically everything from 400 to 700 nanometers, as well as a little bit beyond that, a little bit of far red. When it does that, that energy is kind of transformed and it's moved along through processes in photosynthesis, but eventually it gets to this next big protein complex called photosystem 1. And when the energy gets there, it can get a little bit of boost, right? So from more light energy coming on or coming into that system, it can boost the flow of energy that's happening uh, through photosystem 1. And photosystem 1 is different from photosystem 2. Photosystem 1 is able to absorb far red light much more effectively than photosystem 2. So in a situation where, like, let's say that first step happened, you absorbed a bunch of light and that energy was transformed, and specifically it harvested an electron from water, and that electron is moving through the processes of photosynthesis. If that electron starts to slow down and kind of lose its momentum, then you could give it a boost by applying far red light and re-energizing that thing and helping it move through the rest of the processes. Does that make sense so far?
I mean, it's a little over my head. I get what you're saying a little bit in the sense that having a little bit of far red, my takeaway from what you're saying is having a little bit of far red might be beneficial still, but maybe
Yeah,
I'm
yeah, it's
misunderstanding that.
yeah, it is. It's a pretty tricky thing to describe, and candidly, for years I've been trying to find a better analogy for this, and I don't have one. So I'm going to keep working on that. But I guess where I'm going with this is um, that boost with far red. It's really not necessary most of the time. Most of the time, that electron is going to move happily through the light reactions of photosynthesis and ultimately end up making biochemical energy for the plant to then make into other just plant stuff. There are rare but theoretically possible situations where you do end up with the kind of a bottleneck, like that electron isn't flowing through photosystem 1 very well. And in that situation, then having a boost with far red light uh, could give you a net photosynthetic rate greater than if you were to try and do the same thing by adding just par light. So the reason I say it's not commercially relevant is because those rare scenarios where I'm talking about where far red is going to do something really good for you as far as photosynthesis goes, with cannabis, you have to be at really, really high light intensities to arrive in that situation. And if you're not up at these really
Mm.
high light intensities where you are driving the first half of photosynthesis really, really hard, um, far red's not going to do a whole lot for you. That more par light can't do for you.
So this is more of a crop specific thing rather than, so you're not saying the Emerson effect isn't important in plants. You're saying in cannabis, the requirements because of the crop are it's a highlight plant or whatever.
Mhm.
Um, you're not going to see a real noticeable effect like you may with, I don't know, lettuce or tomato or some other
Yeah,
crop. Is that essentially what you're saying?
that is essentially what I'm saying. And again, it's a shame. Well, it's a blessing and a curse how complicated photobiology is because there are other things at play here too. Like in lettuce, for instance, not only are you going to get to the point of photosynthetic saturation at lower intensity, but you're also going to do things like expand the leaves when you add far red, such that you get much greater light interception. Uh, so the combination of using a little bit of far red with lettuce to drive photosynthesis better, but also have greater leaf area, which means you're intercepting more light, which means you have more photosynthesis, which means you have more yield, right? That's a really, really different situation than what we experience in cannabis.
Mm, okay. All right, that does help explain better. Thank you. Well, let's move on because I had a couple other topics, and we've already been talking for a while, but I wanted to get your answers on them. Lighting, lighting location. So I'm hearing more and more about under canopy versus inter canopy versus top lighting exclusively. Um, I am going to try actually in my grow. We haven't talked about this, but in my next grow, I'm going to do a comparison of top lighting and a combination in one bed, and then next to it, I'm going to do another bed of under canopy and top lighting. And I was thinking of keeping the par levels equal between the two. So let's say I do, let's just to make the numbers math right now, 1,000 ppfd at canopy on the top lighting side. I would do maybe 800 and 200 in terms of top and bottom on the under canopy lighting. What are your thoughts on that, and how does what I guess what's your let's back up. I'm getting ahead of myself. What's your opinion on under canopy versus inner canopy versus top lighting? Let's just start there and then we'll get to my scenario
Gotcha.
next. Sorry. I got ahead of
Yeah.
myself.
No, no, I believe me, I get it. Um, the short answer is I like these things. Intercanopy or subcanopy or under canopy, whatever you'd like to call it. These are good things and people should do it. And not just in cannabis, but this is something that should be practiced in any commercially cultivated plant that has a very dense or tall canopy. The really, really short and sweet explanation of this is that the more uniform an environment you create, the more uniform a plant you will get. So do it. And I guess to give kind of a more kind of practical answer than that, right? If you create a more uniform canopy with cannabis, you will also have a more uniform bud volume and bud mass, which means that you're going to get a higher market value for all of your
So
buds versus just like A grade at the top.
yeah, so as I understood it being explained at PhotoX, was by splitting up the light, by having under canopy light as well as top canopy light, I'm able to raise par levels with less risk of photo bleaching. So I can hit that higher yield by getting the 1% more energy equals 1% more light um, onto the leaf surface, onto the plant, and split it up. And by splitting it up, not only could I potentially increase my yield, but I can also increase my bud quality in the sense that those lower B grade buds that aren't getting enough light, now I'm lighting them from below, which I'll be honest sounds a little weird to me because I'm hitting the underside of the leaf now instead of the top. But maybe that doesn't matter. But what I'm going to get is a much higher percentage of A quality buds, as we call them in the industry, versus the lower quality stuff that we don't really want.
Yeah. Yeah. I mean, you're fundamentally correct. There are a couple things to unpack there. So first of all, when you're thinking about intercanopy light or you're thinking about under canopy light, you can think about it as a means of adding light, or you can think about it as a means of redistributing light, right? So if you are adding light, then you are going to have an increase in yield, right? And it just goes back to that 1% more light is 1% more yield kind of thing. If you're at 1,000 micromoles right now and you add 200 micromoles or 300 micromoles of sub-canopy light, you will increase yield 20 or 30%. And that is an important note, right? Because we've had a little bit of, um, I don't want to say conflict in the market, but I would say miscommunication in the market. We've had some people come back to us and say, well, Fluence, you guys are saying that if you redistribute light to within the canopy versus the top of the canopy, you don't increase yield. But everybody else in the industry is saying that if you use their sub canopy light, it's going to have like this amazing 20, 30, 40% bump in yield. It's like, yeah, to be clear, we agree with that. If you are adding light to the canopy, you will see that bump in yield. But if that's your only objective, you might as well just do it as top light because the plant can take it, and then you won't have any kind of like lighting infrastructure down on your table that could be in your way, right? But if
Mhm.
your goal is to increase yield while also improving bud quality and bud uniformity, that's where the value of intercanopy or subcanopy light really is. And if you are power limited, right, you only have so much electricity going into your facility, but you'd still like to improve your bud quality and yield. I'm sorry, bud quality and bud uniformity. Then we'd say, okay, maybe your energy is better utilized taking some of your top light away and sticking that down below the canopy. Now, to your point about how it feels maybe not so intuitive to light buds from the bottom, yeah, I'm right there with you. It does feel weird. Um, the reason it works, right, is that we have to remember at the end of the day, plants produce sugars in their leaves, right? And then those sugars are translocated to sink tissues, right? So you probably have heard of source and sink tissues. Leaves are your source tissues. They're like the solar panels of the plant. They catch light and they convert it into sugars, basically. Those sugars don't stay in the leaves. They are translocated through the phloem to sink tissues that are actively developing. In the case of cannabis, that's the inflorescences or the buds. So it really doesn't matter which orientation you light them from.
Hmm. That reminds me, the sink tissue thing reminds me of I think also Allison Justice did some research. And again, this was like 2018, 2019. This was a long time ago, talking about how certain lower PPFD levels created leaf tissue that was sink tissue when it was below like 200 or 400 ppfd in flower. I think 200 off the top of my head. And again, don't hold me to any of this, obviously, if you're listening to this podcast. But um, the idea being then, if I light it from below, that the leaves closest to those buds are really what's driving that bud size or inflorescence maturity. Is that essentially the hypothesis here?
Truthfully, I can't speak to that in detail. We haven't looked at that. I know there's research on other crop species like tomato, where they've looked specifically at carbon translocation um, to kind of identify, like what are the leaves that are most productive and most relevant to, the sink biomass. Um, Sorry, I'm not explaining this very well. I guess maybe what I would just tell people to do is if you're interested in this, look up research from the University of Guelph by Bernard Grodzinski and Jason Lanoux is another author. They used radio labeled carbon to feed the plant carbon dioxide that they could visualize, right? So with certain technologies, they can literally see the carbon go into the plant, through which leaves it goes into the plant, and where, like, what tissues does it move through the plant and where does it end up, right? And in that research, they could tell you more definitively, at least in tomato, whether or not the leaves closest to that sink are the thing driving yield, or whether it's really just all of the leaves. But
Hmm.
with cannabis, I really couldn't tell you. I could only guess.
Yeah, and then on that note, intercanopy versus undercanopy. Um, I have this like impression, and I don't know what it's from, but something at PhotoX, my takeaway was that undercanopy was somehow superior to intercanopy, but maybe I made that up.
Um, if you made it up, you're right. And I don't want to just generalize that for all people at all times, but Generally, what we've seen in our research is that for people growing in the cultivation styles that we see most commonly in North America, on kind of like a four by whatever table with like 3 or 4 rows of plants and fairly dense canopies. Generally, in those scenarios, we see for the equivalent energy yield of about 7.1% greater with under canopy light than with inter canopy light. And
Okay.
we
Yeah, I didn't
believe
make
that.
it up there. I was
Yeah,
remembering.
yeah,
Okay.
no, you're right on. And the reason I'm putting all these caveats on it is because this is not true for all cultivation styles, right? To give you one extreme, we had one grower that was interested in more distributed light, whether intercanopy or under canopy, and their cultivation style much more closely emulated what you would see in a sort of like Dutch vine crop greenhouse, where the plants were in hanging gutters, and there was maybe a meter between each gutter. So you have like these nice long, even rows of plants. What they had was incredible uniformity in their crop. It was really, really cool to see. But this is a greenhouse environment that I'm talking about, and they had such good light penetration just from overhead supplemental lighting and sunlight that there really wasn't a whole lot of benefit to them for adding sub canopy light because light was already getting down to those lower leaves, lower branches. In their case, intercanopy light was way, way better. They were still adding light, they were still getting a slight increase in bud uniformity, but again, even just from like practical things like installation, intercanopy was way easier for them. And they
Hmm.
didn't have to figure out like where am I going to mount a sub canopy light and things like this. And ultimately, again, it goes back to just the more uniform a light environment you can create, the more uniform the plant will be. And so people have to kind of determine for themselves, or with our help, of course, what makes sense in their facility.
All right, two last questions because I know we've been going a while. One of them is, have you ever seen any issue? I assume no, with photo bleaching or too high of light intensity in with traditional under canopy lights. Like, let's just stick with the ones that Fluence makes for the sake of discussion today. Are there any risks or things people should be aware of when they're installing them?
Yeah, I think the most interesting thing that we've seen is that as it pertains to photo bleaching, um, we don't seem to see it, frankly. So like we we have implementations of sub canopy light that we've tested and that we provide our customers now, whether it's they want to do like a 300 micromole install or they want to do basically double it up and have a 600 micromole install. And what we see is that again, when you're applying like a higher red spectrum at those intensities with sub canopy light, we don't get bleaching, right? And we theorize around why this is, but frankly, we don't know exactly why this is just yet, and we're still continuing to explore that. What it means for growers, though, is that they can use a more efficacious spectrum in their sub canopy light than they can use with their top light. And that's kind of cool, right? So it's really at that point, it's just a matter of, you know, if they care about workplace ergonomics, because some people, like reasonably so, right? They don't want to have a pink light shining up into their canopy and potentially into their face.
Yeah.
Versus when they could just work with like a white light and it's easier to scout the plants and scout pests and things like that and just generally have a slightly more comfortable work experience. Uh, but anyway, again, it's a very cool thing from a photobiology standpoint to know that you can use different spectra depending on where you're radiating the plants from, and it's nice to be able to offer customers and growers at the end of the day that flexibility.
How are we pruning or maintaining our crop differently when we're using under canopy lights versus just strictly top lighting? Because when I top light, I I take my par meter and I work my way through the lower canopy and I say, okay, if it's getting less than, and I arbitrarily 200, 250 ppfd, it's probably not doing a whole lot of photosynthesis.
Mhm.
Again, this is my own estimation here, and I'll remove those leaves. But now, if I have lights coming from below, am I going to want to prune dramatically different? Or for my experiment, should I prune the two plants the same just to eliminate that variability?
I think that if you asked 6 different people on my team, you'd probably get 6 slightly different answers. And so,
Okay.
what I'm going to do is say that we don't definitively know. My working hypothesis is that if you have sub-canopy light or under canopy light, and you're lighting those leaves. Sorry, I'm not being very articulate right now. I think you need to prune less. That would be my working theory right now, because you are making those leaves that otherwise are shaded and ineffective. You are now giving them a task. You're now putting them to work.
The lower leaves. Yeah. So we
Yes, that's
still
right.
would want to prune the middle of the canopy to allow for light and air like we would normally, just for pathogen risk, microclimates, all of those
Exactly.
things.
Yeah. Yeah. You can never do away with pruning, because if you end up with like a really high humidity environment, which is what you would get if you didn't prune, yeah, you are inviting all kinds of pathogens, and that's going to be a bad time.
So, okay, last question. And this is selfish. This is my specific setup. If you were setting up this experiment comparing top lighting versus top and under canopy, and would I want to maintain the same par levels, and where should I set those at? Do you think, for an experiment like that, or if someone wanted to do one at home, similar to what I wanted to do here, to see if it's worthwhile?
Yeah. Um, Step one is decide what your goals are. If your goal,
Let's target 1,000 ppfd for this conversation.
sure. Okay, so you want to keep 1,000 ppfd between all your treatments?
I think so. I want to be able to say, is under canopy lighting worthwhile? Like, is it going to increase the quality of buds that I'm producing with, but so I'm also limited. You don't know all the information, obviously. I'm limited electrically. So I
Okay.
couldn't just say, let's do 1,000 and compare it to 1,300 or something on the other side by just strictly under canopy lighting. Um,
Yeah, no, I understand now. So that is a great consideration, and you're not going to be the only person in that boat. So for someone who is capped on electricity, and you're just trying to say, should I redistribute my light to increase quality and uniformity? Um, yeah, I think that's a great experiment. The way I would do it is I would normalize on um, PPF and not PPFD. Do you know what I mean by that?
no,
Okay.
please
Okay.
explain.
Yeah. So PPFD stands for photosynthetic photon flux density, and it describes how many photons are hitting an area every second.
Yeah. Okay.
PPF stands for photosynthetic photon flux. And PPF is the metric that describes how much light is coming out of a fixture, right? So, like at Fluence, or really any other lighting manufacturer, for instance, we have to report PPF and say this is all of the light that comes out of this fixture, regardless of where you put it. And this is important because, again, this is kind of complicated, and I have slides to go with this. So if anyone's really interested and wants to follow up with me to kind of understand this better, I'm always
Mhm.
happy to connect and kind of go through this in more detail with graphics and everything. But when you have PPFD measurements, we all know how to do that at top of canopy, right? You go in with your power sensor, your quantum sensor, whatever. You move it around at top of canopy, and you say, okay, well, this is the PPFD that I'm getting. Great. When you have an under canopy light, or let's say an intercanopy light, where do you do that measurement? Right? If you have an intercanopy light, do you stick the sensor beside the light, or do you stick it 8 inches away from the light, or do you stick it
I mean, that's a very accurate issue. I guess I'm wondering if if I'm doing under canopy though, couldn't I just measure it the same way and assume that that canopy is,
like a flat plane kind of thing?
yeah, though as I say this, I'm thinking about the fact that the lighting, under canopy lighting, is like a simple tube. And so I assume the uniformity is going to be lower than my multi-bar light up top,
Yeah,
but
and
maybe
again, it,
that's
it
not true.
very, very much depends on which under canopy light you go with. Again, not that I'm here to just hawk our products, but like that is one of the distinct advantages that we wanted to build into our under canopy light, because what we'd been seeing in the market was that it had a lot of the products out there had a relatively narrow beam angle,
Hmm.
meaning that you would get pretty low uniformity, and we thought it was important to try and improve upon that. So, I can't speak to what you've got there, but what you could do is you could just try and treat the bottom of the canopy as a uniform calculation plane, just like you would do at the top of the canopy. But again, what I would encourage you to do is look up the PPF of the fixtures that you have, And so, you go down to the company's website and look up their spec sheet, and it'll say PPF equals whatever.
Mhm.
And for a study like this, I would normalize on that. So I would say, okay, well, I have 3 Fluence Viper lights on top, for instance. I've got these 3 Vipers. Fluence says their PPF is this. So I'm going to sum all that up. And that is my target PPF. Now, in treatment number 2, where I want to have top light versus, I'm sorry, treatment 1 is just top light. Treatment number 2 is top light and under canopy light. So I'd say, okay, I'm going to subtract 30% away from my top light PPF, not PPFD, but PPF based on the fact that I have these 3 lights there and each one delivers a PPF of whatever. I'll subtract that away and I'm going to deliver that to the bottom of my canopy with under canopy lights, that same
Mhm.
total PPF. And that's how I would make the comparison. The reason I say that is because, again, quantifying PPFD for a subcanopy or an intercanopy light is quite difficult. And you can end up with some really, really misleading data. So we work with PPF instead, but that also comes with its own assumptions. When you work with PPF, you are assuming 100% utilization of that light, which also we know isn't true, but we think it's a
Mhm.
closer and more fair comparison than PPFD.
Okay, so if I said the PPF of the light was, I don't know, 300, I
Sure.
assume the numbers calculate the same. So if it was 300 and I was doing 1,000, that means I'm going to give approximately 700. I'm going to
Yeah,
measure approximately 700 ppfd with my light meter on the top canopy to approximate what I'm approximating as 1,000 ppfd on the other side. Does that sound like a reasonable way of approaching that?
it is. And I mean, again, I recognize that a lot of what I just described might be too technical and complicated for most people. So what you said, where you just say, well, I'm just going to do a 700 and 300 split. Yeah, that is a reasonable, if less precise
Yeah,
approach
so
for
not
the
as
for the
rigorous.
average.
And I wouldn't
Yeah.
necessarily draw any strong conclusions from it. This is more just a real world scenario comparing the two options in my specific, because I wanted to experiment with it. And I just want to go back and then and look and say, oh my gosh, so now I have all these A quality buds over here. Maybe my yield is comparable. Maybe it's not, but that to me is interesting information to have, I guess, as a grower. And that was why I wanted to experiment with it. Ultimately, if I didn't have any power limitations in my current space, I would much rather just run, let's just say 1,000 ppfd across the top on both, and then under canopy on one, and just see if I do get a 20 to 30% yield increase, because that's massive. So if someone is listening to this conversation, that would probably be a more useful trial to run given no electrical constraints or massive electrical costs. Because I am hearing people report pretty big, significant increases in yields by adding under canopy lighting. So
Yeah, and as they should. I mean, again, they're adding energy. So whether they do it as under canopy light, whether they do it as top light, if they add 20 to 30% more light, they're going to get 20 or 30% more yield, which is awesome. It is a huge jump.
yeah, on that note, one of the growers I was talking with at PhotoX, they happen to be I think the largest indoor facility in the world, was saying that they do get a little bit of photo bleaching, but they offset that by their yield increases, and so they're okay with it. It's not the end of the world, and that can go into another product that they make, so it all gets used in the end. And I thought that was a really interesting perspective, because you go on social media on Instagram and no one, you never see a photo bleach bud, because that's not what people want to see. But the reality of the conversation we've had today and the research that you shared is that um, maybe an optimal grow would actually have a few buds with photo bleaching happening in there, because that tells you may be closer to optimizing your yield without sacrificing anything on the secondary metabolite or cannabinoid side. Just as a broad conclusion for folks who check out this podcast.
Yep, I agree.
Cool. Well, thank you so much for all your time today, even through all these technical difficulties. I had a wonderful conversation. I learned a ton, and I hope to catch up with you again soon.
Yeah, it's been a great pleasure. Thanks so much, Dad.